now that everything's set up and we're in the classroom and everything else. All right, sorry about that, everybody. We were locked out of the classroom and had to wait on somebody to come in and get it open for us. Today, we're going to pick up where we last left off. Last class, we were talking about odd and even functions. I said that even functions are functions such that f of x was equal to f of negative x. These are functions that are symmetric about the y-axis. Then there were odd functions. These were functions that negative f of x is equal to f of negative x. And these things, they're not symmetric across the y-axis, but the first quadrant and the third quadrant are symmetric. Does that make sense what I mean? So when we reflect across the y-axis and then down across the x-axis, we have the same image. Make sense? And in that way, they're symmetric across the line y is equal to negative x. Cool? So I think it'll be easier just to draw an example of these. Right? No, not close enough. It'll be easier if I just go ahead and draw a cubic. All right. So just as two examples, one of an even function, one of an odd function. Notice the odd function, if you were to reflect across the y-axis and then across the x-axis, they're the exact same graph, right? Here, with an even function, if we're to reflect across the y-axis, we get the same graph. Yeah. So these things have some special properties, and they all come from the way area behaves given these reflections. If we were going to take some a value and some negative a value, find the area between these x values. But notice what happens. We could consider just this part here and multiply it by 2, right? So because of that, given an even function, the integral from negative a to a of an even function is equal to 2 times the integral from 0 to a of that same function. Make sense? And this happens to be because of symmetry. This thing is the mirror image across y, so the areas are going to be the same in both directions. So for that reason, we can say, hey, it's enough just to calculate half of this and multiply it by 2. Cool. Now, a point on this, we do have to have it being integrated symmetrically across 0, right? So it's from negative a to a. Similarly, over here, notice what happens. Here, we've got a. Here, we've got negative a. Well, these areas are equal in magnitude, but they differ by a sign. This is going to be negative area. This is going to be positive area. So they're going to add up to 0, right? So because of this, we know negative a to a of an odd function, this thing is going to come out to be 0, which is convenient. Because it means in your homework, if you look at a function and you say, hey, I think that thing's odd, look at the graph and you check it, and it is odd, then you know the integration is going to be 0 if it's symmetric across negative a to a, right? Or if it's integrated from negative a to a, I should say. So as 2 quick examples, let's consider x squared and x cubed. Because I need to check. Let me see something really quick. Yeah, okay, cool. Okay. So this thing, this x squared, it's symmetric from across the y-axis, right? So because of that, the integral from negative 2 to 2 of x squared dx, we're going to be able to rewrite. Before we rewrite it, let's actually calculate it out from negative 2 to 2. So this thing is going to be x to the third over 3, negative 2 to 2. Now, this thing is going to evaluate out to be 2 to the third divided by 3 minus negative 2 to the third divided by 3. This is going to come out to be 8. This is going to come out to be 8. What's happening here? What is happening here? Because I just did something wrong, didn't I? Oh, no, I didn't. Okay. This is going to come out to be 8. This is going to come out to be negative 8. My mistake. I was trying to square it in my head and drop off the sign. So what we have is this thing is 8 to the third. I mean, my mistake. 8 over 3 minus negative 8 over 3, or 16 over 3. Now, if we had just used the trick we were just talking about, the property that odd and even functions can be integrated particular ways, we had used that instead, some of the arithmetic here would have dropped out. What I mean is, we had said, all right, this thing from negative 2 to 2, the integration of x squared with respect to x is equal to 2 times the integral from 0 to 2 of x squared dx is equal to 2 times the integral of x squared is x cubed divided by 3 from 0 to 2. This is going to be 2 times 2 cubed divided by 3 minus 0, right? Well, this is going to come out to be 2 times 8 over 3, or just 16 over 3. So it's not immediately clear here how it's convenient, but notice here we have a 0 that pops up, right? So for more insane polynomials, for more insane calculations, there's less work on the back end here, because we can just plug in a 0 instead, right? And then multiply by 2, and that's pretty straightforward. Here, we can imagine a case where we might have a whole bunch of weird values that we have to turn into the same fractions and da 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 da. It becomes a headache pretty quick. Get what I mean? Now, in the case of x cubed, the integral from negative 2 to 2 of x cubed with respect to x is equal to x to the 4th over 4 from negative 2 to 2. This is going to be equal to 2 to the 4th over 4 minus negative 2 to the 4th over 4. This is going to come out to be 16 over 4 minus 16 over 4. That was a lot of work just to get 0. If we had instead said, hey, this thing is an odd function, just because of its behavior, right? It reflects across a particular way. Well, because of that, we know the integration, when it's symmetric about 0 like it is, we know it's going to come out to be 0. I don't have to do all this work. I can just say, yeah, it's 0. Take advantage of that property. So they just show how this applies directly. If you notice that x squared is even right away, you can rewrite your integral accordingly. Take advantage of the fact that you have a 0. It's a whole lot less work for you. Then you get 16 over 3. X cubed is odd. So there is no work. It's just 0 because we're integrating from -2 to 2. Now, a point on this really quickly. We can use this to make other problems easier as well. And it may not be immediately obvious how we're going to do that, but let's say instead it was from -2 to 3. Because our function is odd, we know from -2 to 2, our function is going to integrate out to be 0. So we only need to worry about 1 to 2. Or I mean, 2 to 3 is what I mean to say. Does that make sense what I mean? So we can use this to break up our integrations as well. What I am trying to say here is, in the case of x cubed, if we wanted to integrate from, say, -2 to 3 of x cubed dx, we can break this up into two different integrals, one from -2 to 2 of x cubed dx, plus another one from 2 to 3 of x cubed dx. This thing is going to be 0, so we only have to calculate this thing. So sometimes we can use this to also make other calculations a little bit easier for us, other than just nice, smooth, symmetric ones. And we can do the same trick with even values as well. Cool. So in the case of the other one, let's say it was x squared. Well, now we can rewrite this as 2 from 0 to 2 x squared dx plus the integral from 2 to 3 of x squared dx. And again, makes the work a little bit easier on us. So we can use these in a couple different ways, but the point ultimately here is making these observations and getting used to them, becoming a pro with them, really does drop out a lot of work for us. Mathematicians love to use these two properties. So, having said that, next thing we're going to talk about is the amount of an annuity. The amount of an annuity is calculated as e to the r t, the integral from 0 to t, c of t times e to the negative r lowercase t dt. Okay, now I hate the notation here. I hate it, I hate it, I hate it, I hate it, I hate it. I hate it because it's confusing as hell. We've got a whole bunch of t's, and it sucks. And I agree with you if you think it sucks. Personally, I feel like we should replace these t's, these capital T's, with a K to make this a lot less confusing for us. And what this K value is the end of the period of time. It's just some constant that's important to the problem, right? It tells us when this annuity ends. Cool? But otherwise, everything else is the same. Okay. So looking at a quick example of this, here we deposit $2,000 each year for 15 years in an individual or in an IRA, paying 5% interest. And we want to know how much we'll have in the IRA after 15 years. So first, CT in our example problem is equal to 2,000. Capital T, or as I wrote it over here, K, is 15. R is 5%, which written as a decimal is going to be 0.05. So the amount of this annuity is going to come out to be E times, or E raised to the 0.05 times 15, that quantity times the integral from 0 to 15 of 2,000 times e to the negative 0.05 times 15, or my mistake, times t dt. So from here, we've got the integral set up. We can solve this, right? Now all we've got to do is rearrange some terms. We can pull out that 2,000 right away. Or we could use it to rewrite this in terms of u sub and figure out what that integration comes out to be. Then take the difference at our bounds. And do the arithmetic. Make sense? So really, this is just another tool. This is actually going to be a really useful tool, something y'all should know moving forward in life. I imagine not many of y'all have started thinking about IRAs. You should. It's a good thing to start thinking about early, so you have a whole bunch to retire on. Having said that, let's jump on to the next problem. Next problem is a concept check. For the folks at home following along, this is page 43 of the notes. And these are the week 13 slides under exam 4 in the course material tab on Blackboard. So, jumping into section 5.4. We've been talking up to this point about the area underneath a curve. But what about the area between two functions? What about something like one of these particular cases I'm about to draw? Today is really not my day. Just broke my jaw. Lame. Okay, cool. It happens. So, how would we find the area between these two functions and given a and b x values? So what I'm asking is, how are we going to find that area? Well, one thing we could do is say, let's take the area underneath g of x, and let's take the area underneath f of x and subtract them, right? So the area from A to B under f of x dx minus the area from A to B under g of x dx. That's going to be equal to, we can rewrite this as the area from A to B between f of x and g of x. And that is the equation for this area up top. So to give a better idea of what we're doing here, let's jump to the next slide. What we're doing here is we're saying we've got two functions, f and g. We want to find the area between them. So first, let's find the area under f. Well, notice they both have a shared set of area. Everything under g and under f, right? So if we remove just the stuff that's under g, we get what's in between them. And that's what we're saying here, is that this area is equal to the area under f minus the area under g. And we can rewrite this integral as the integration from a to b of the difference of f and g. Now there's an assumption here that's built into this problem and the way it's written. And excuse me, that is on the next slide actually. Cool. Given that g of x is less than or equal to f of x on our interval a to b, the area between them can be written as the difference f of x minus g of x integrated from a to b with respect to x. So the setup of this says, whatever that first term is on your boundary or in your domain or in your boundary from A to B, it's got to be the thing that's greatest. Make sense? Okay. So with this in mind, this first example, we've got something different going on. Draw it up here. This is x squared equal to y. The other one is just x equal to y. Yes, I know, my graph is all sorts of crooked and not exactly to scale, but it's going to highlight the idea here. What we want to do is we want to find the area between these two functions up to x equal to 1 from x equal to 0. So we're trying to find this area here. My mistake, it's x squared plus 2. Plus 2 is equal to y. We're finding this area right here. Pulling it out of the graph, what it looks like is something like this. Right? Really weird shape. find this area, we're just going to integrate the difference between them. X squared plus 2 is always greater than x. So because of this, our integral is going to be from 0 to 2, I mean 0 to 1, my mistake, of x squared plus 2 minus x integrated with respect to x. So we're going to rewrite this as the integral from 0 to 1 of x squared minus x plus 2 dx. From here, we're just going to do the calculus like we've been doing, right? You're going to integrate this out. This is going to give us x cubed over 3 minus x squared over 2 plus 2x. We're going to take the difference from 0 to 1, right? Since the rest of this is just algebra and arithmetic, I'm going to leave it as it is and jump to the next example. Now, the next example changes this problem considerably. It doesn't seem like it does, but it does. It changes it considerably by just changing one sign. I'm just changing the sign of x squared here. I'm going to rewrite all of this. This is now going to look something like this. Go through 2 x squared, my mistake, 2 minus x squared is equal to y. And everybody's favorite, x equal to y line. Now here, we want to find the area bounded by these two functions. So what does that mean, the area bounded by two functions? Well, let's check out what's happening here. You notice these two functions intersect each other at exactly 2 points. There's a space that they both kind of block in, right? That's the area we're going to find. We're going to find this area inside of here. Now let's start setting up our integration. We know this is going to be the integral of, well, 2 minus x squared is always on top, right? So we know it's greater. Cool. That's going to be, let's write it like this actually, green, 2 minus x squared minus x dx. Now the question is, what are our bounds? What is a and b here? Look carefully at the graph. What does x equal to a and x equal to b represent? Exactly. They're the points in which our two functions intercept each other, where they're equal to each other. So we can start by saying, okay, at these 2 points, A and B, we know x is equal to 2 minus x squared. Okay, well, if that's the case, then we can rewrite this by subtracting 2 minus x squared from both sides. We're going to get x squared plus x minus 2 is equal to 0. All I did was subtract this from both sides. Now this thing can be factored, right? It factors as x plus 2 times x minus 1. That quantity, the product of those two, is equal to 0. So looking at this, A is equal to -2, and B is equal to 1, right? So we can come over here now and say, cool, let's add in our balance. Now, I can simplify all this a little bit. This becomes the integral from -2 to 1 of 2 minus x squared dx. I meant to disconnect that. This is a rough morning, guys. Man, I need a coffee now. I deserve it. Okay. So from here, we're just going to do the integration like we normally would, right? There's nothing fancy going on from this point on. We're going to say this thing comes out to be 2x minus x squared over 2 minus x cubed over 3. We're going to take the difference from these things calculated at -2 and 1. Okay, so looking at this problem, we're finding this interior area, right? This is the area bounded by the two functions. One of the things we're going to have to do is find out what the x values are where these two functions intercept each other. That's what we've done over here in yellow. We set the two functions equal, then we rewrote them and found that they were equal to 0. We rewrote them, right? We said, all right, rearranging these terms, solving for x, we're going to get that x squared plus x minus 2 is equal to 0. Well, this thing factors out nicely, so we can find a and b pretty easily now. Yeah? So we've got our a and b here. A is -2, b is 1. Now, it comes down to identifying which function's on top, which function's on bottom. 2 minus x squared was on top, and x was on bottom. So we're going to have the integration from -2 to 1 of 2 minus x squared, that quantity, minus x, integrated with respect to x. From there, we do everything the same. Looking at the way they went about this problem, the exact same idea. They started by saying, all right, This is what we want to get to. We want to set everything up based off of this area formula. Now, we need to know what our x and our y, or I mean our x bounds are, right? -2 and our 1. So that's our point here. Plug everything in, rearranging the terms, integrating, then applying the bounds. Everybody cool with this? Well, since we only have a minute, this problem's going to take a little bit of time to go through, I think, isn't it? Yeah, I'm going to go ahead and let y'all go. We'll pick up where we left off today on Monday. There is homework posted in case y'all haven't seen. It's due Wednesday. It covers 5.4 and 5.5. So we will finish up the rest of that homework material Monday. But then these last 2 weeks, we're going to go over 5.5 and then get into a little bit of 6 stuff. To get y'all started on thinking about 6 material, because what comes next, I want y'all to start thinking about doing this derivative. So since next week we're going to be talking about undoing this derivative, I want y'all to go ahead and start thinking about it. And how we might be able to use it to solve god-awful integrals. Think about how you might be able to use this to solve an integral like that. Okay. Having said that, like I said, I will let y'all go.